Hey everybody, this is Mr. Weiser here. We're going to be covering normal distributions part two. This will be lesson three in module three. Let's get started. The first thing we have to define is a continuous random variable. It's kind of like a random variable, but instead of having defined numbers like one, two, three, it can have numbers that are between values, so like decimals and things like that. So a continuous random variable, don't think of it more as a histogram, think of it more as like a nice curve. What kind of a curve might be considered a continuous random variable? Well, maybe a normal curve. But the general name for these is called a density curve. Density is basically any curve that defines a probability distribution, and it has the area of exactly one underneath it. So a normal curve conveniently fits that, but it doesn't have to be normal. Take this problem, for example. Selena works at a bookstore in the Denver International Airport. To get to work, she can either take the airport train from the main terminal or use a moving walkway that would allow her to get from the main terminal to the bookstore in 4 minutes. She has used the walkway a few times, but mostly has used the train to get to the bookstore, which varies between 2 and 5 minutes. She wonders if it would be faster to use the walkway. The dot plot at the right shows the amount of time Selena has taken to get to the bookstore by train each day for the past 1,000 days she worked. So she basically plotted all her times, and a lot of those times seem to be very straight across. So it's not a perfect box, but it is pretty close to a nice uniform distribution. So since it's considered fairly uniform, we can model this with a density curve. So notice the distribution is uniform. She would like to know the probability of the train time taking less than 4 minutes. She could count all the dots below 4.0 and divide by 1,000, but that's a lot of dots to count. So it'd be time saving to kind of think of this as a rectangle and go from there. So there's a couple things with a density curve like this that's uniform. The first thing you want to realize is it really just forms the shape of a rectangle. So the idea is that a rectangle is always going to have an area, and that area is going to be length times width, or we could also just say base times height. And since we know the area must be 100% of the data, that area is going to be one, we're kind of limited to that height being whatever makes up for the base. So in this case here, since we have a length here that is going to be from 2 to 5, we know that distance is going to be 5 minus 2, which is going to be 3 minutes, which means our height's going to have to be, well, it's going to have to multiply with 3 to give you 1. So if you think about this one, the height times the base being 1, when you multiply them together, you really just have 3 times h. Well, we just divide by 3 and you get a height that's going to be 1/3. Well, it says justify your answer. I think your justification right here is this work. Now, what do you mean by 1/3? Well, it's a probability distribution. So it really is like 0.33 repeating, right? So that height you can think of as 1/3 or, 33.3%. But that coupled with this length here will give you an area of 1. Now we can utilize that to help us answer the following questions. So part B says calculate the probability that it will take less than 4 minutes to take the train, given that it takes between 2 and 5 minutes. So we want to know what's the probability it's going to take less than 4 minutes, given that it's going to be between 2 and 5 minutes, or in this box here. So if we look at the less than 4 minute crowd, that's really over here. As you can see, it's going to be the red dots here, but we're not going to count all those dots. So we're really just going to get this area. Well, let's think about that distance here. This really is a width of 2, because you do 4 minus 2 equals 2. So that probability is going to be the area of that red rectangle. So the probability that it's going to be less than 4 minutes in this box, I'll write the symbol out, less than 4, is really just going to be 2 times 1/3, base times height. Well, that's really going to be 2/3, or about 66%. That's it, folks. 0.66. I guess I'll put another number on there, 7 to round that up. But you're really just getting an area of a rectangle for these. There's really nothing more to it. So now comes the question, should she switch to the walkway or stick with the train? I suppose that's really a personal decision, but if I'm looking just at the numbers and not any other variables to go along with this, I would say because she's two-thirds likely to have a time that's less than 4 minutes, and we know that train is always going to be, or excuse me, that walkway is going to be 4 minutes regardless. Um, you're guaranteed 4 minutes, but I think with this here, you have a two-thirds shot of being less than 4 minutes. I would say switch or stick with the train in this case. Since the likelihood of being less than 4 minutes is pretty great, two-thirds. A uniform density curve is not the most common type of curve. The most common one you're going to see by far is going to be a normal distribution. And you've already studied normal distributions in the previous lesson. So this is really just a recap of them from the probability point of view. So remember this distribution, not all distributions are going to be normal. In fact, most aren't, but a lot of them can be approximated as normal. So you can draw your self-density curves that give an approximate probability distribution modeling a normal curve over what might be really just a histogram. Um, so let's use our normal distribution and all the skills we learned in our previous lesson to help us answer a few questions. All right, example 2, normal distribution revisited, random variable addition. One brand of baby bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water in a randomly selected bath can be modeled by a normal probability distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. Let's highlight that. Let Y be the water temperature in degrees Fahrenheit for the randomly selected bath. Recall that the degrees Fahrenheit is 32 plus 9/5 times the degrees Celsius. According to one source, the temperature of a baby's bath water should be between 90 and 100 degrees Fahrenheit. We are interested in finding the probability that this happens on a randomly selected day when the baby safe setting is used. So for part A, we want to find the mean and standard deviation of Y. Then for part B, we're going to determine the probability that the bath water has a temperature between 90 degrees and 100 degrees Fahrenheit on a randomly selected day when the baby safe setting is used. Part C, based on this answer, should a parent feel comfortable using the baby safe setting with this brand of baby bathtub? And part D, what is the 99th percentile of the bath water temperature in the baby safe setting used? Now, you might want to screenshot this or write these down if you don't have the booklet with you so you see all the parts. We're going to go one part at a time. Part A, find the mean and standard deviation of Y. Remember, Y is the water temperature in degrees Fahrenheit. So we're going to use this formula to help us solve it. The degree Fahrenheit equals 32 plus 9/5 degrees Celsius. We'll want to plug in our degrees Fahrenheit for the mean. And then if we plug that in, we're going to do all the operations with 32 and the 9/5, and we'll get our degrees Fahrenheit. So we're going to plug in the Celsius, get the Fahrenheit. And in this case here, your degree Fahrenheit is going to be 93.2 degrees. We're going to want to also plug in our standard deviation. Now recall, adding or subtracting does not affect the spread. So that 32 should not get added in this case. So make sure you cross that out. Now just plug in your standard deviation for your degrees Celsius. And you're going to get 3.6 degrees Celsius as your standard deviation, degrees Fahrenheit. Now that we have our mean and our standard deviation, we can now use normal calculations in degrees Fahrenheit and answer some questions. Let's go on to part B. Part B says determine the probability that the bath water has a temperature between 90 degrees and 100 degrees Fahrenheit on a randomly selected day when the baby safe setting is used. Well, we're going to still treat this as a normal distribution. Since we started with a normal distribution, multiplying, adding, and subtracting, it's not going to change the fact that it's a normal distribution because the shape won't change. So we're going to draw a normal curve. We're going to label it N. Remember, your mean's going to go first, so 93.2 degrees and 3.6. Put the mean in the middle. I don't bother counting out standard deviations. I really just answer the question and highlight my boundaries. So I want to go between 90 and 100. So 90 is going to be below 93.2 and 100 is going to be somewhere above it. It doesn't have to be super precise, but you want to shade the appropriate boundaries and put your left and right boundary here. So we're going to calculate this probability. We're going to use normal CDF. So we're going to go into our calculator and we're going to find normal CDF and put in our inputs. So remember, you're going to hit second vars, go to option 2, normal CDF. Your lower bound in this case will be 90 and your upper bound will be 100. We'll put our mean and standard deviation that we calculated in, so 93.2 and 3.6. And we'll go down to paste and we'll get our probability. Now let's make sure we write all this out. The probability that the bath water is going to be between 90 degrees and 100 degrees Fahrenheit on a randomly selected bathtub, or randomly selected day when the baby safe setting is used, is about 0.7835 or 78.35%. Part C. Based on this answer, should a parent feel safe using the baby safe setting with this brand of baby bathtub? Explain your answer. Well, if you had a baby and you wanted to make sure their bathtub temperature was safe, would you feel confident with a 78.35% chance of that happening? In this case, I probably would not. Think about it this way. If you take the complement of that and subtract it from 1, the probability the temperature is not safe is about 21.65%. In this case, as a parent, that probably would make you feel uncomfortable, so the parent should not use that. Part D, last part. What is the 99th percentile of the bath temperature water in degrees Fahrenheit when the baby safe setting is used? Well, let's clear this stuff out. So the 99th percentile is going to occur when 99% or less um, of the data is below a certain point. So if I draw myself a normal curve, that 99th percentile is going to be somewhere over here. 99% of the area below should be shaded. So I know that my area should be 99 or 0.99. And my mean is still going to be 93 point, what was it? 93.2, 93.2 and 3.6 for your mean and standard deviation. So we're going to calculate the 99th percentile using inverse norm. We'll go into a calculator. Remember to access that, you'll do second vars, and you're going to do option 3 this time. Your area is going to be 0.99. Keep your area going to the left. So the default on this calculator is going to be left. We'll leave that. 93.2 for your mean and 3.6 for your standard deviation. That'll give you a 99th percentile temperature of 101.57 degrees Fahrenheit or approximately 101.6. We're going to round that up to 101.6 degrees Fahrenheit, and we're going to go ahead and write our inputs that we did in the calculator. Remember to receive full credit on these, make sure you put your calculator inputs with your clear defined parameters, your mean, your standard deviation, and list out your answer in full detail. So 99th percentile is going to be 101.6 degrees Fahrenheit. Make sure you include units on that because it's not just a probability, but it's an actual thing. What happens when we combine two random variables? Well, just like with probability, with normal distributions, you're going to have the same properties. So when you add two random variables together, you're going to add their means. When you subtract them, you're going to subtract your means. Look at these simulations over here. We have two separate random variables, and you can look at their combined when you do add them together. If you have two separate means, 2.5 and 1.5, when you add them together, your combined mean is going to be right around here, right around 4. And in fact, that's going to be the mean when you combine two random variables with those means. We simply add them together. Also, for the other one, for that red one there, since this is going to be the difference between those two, you would subtract them, 2.5 and 1.5, and that difference is going to give you about 1. And you can see that right here, 1 is right in the center of that distribution. So that's exactly as you would imagine it. Remember, the notation is important. So I do the mean of x plus the mean of y equals 2.5 plus 2.5 equals 4, and the mean of x minus the mean of y equals 2.5 minus 1.5 equals 1. Now remember, the variances work differently. You're going to square the standard deviations to get the variances. So remember, this is going to be the variance. And notice that the spread is going to be the same for both of these. One's not smaller than the other just because you subtracted them. So that spread's going to get bigger regardless. So with the addition one and the subtraction one, you're both going to do addition. But remember, we add their variances. So we do our standard deviation squared of x plus our standard deviation squared of y. And that's going to be 0.9 squared plus 1.2 squared. And whatever that is equal to be will be your variance. The same thing is going to be true for difference. So even though it's a difference there, we're still going to add those because that spread is going to get bigger. So the standard deviation of x squared plus the standard deviation of y squared. Same math, same answer as a result. So let's use our calculator to come up with that answer. So you'll see the variances for their combined distributions are both going to be 2.25. So once you square their standard deviations and add them together, then you can simply take the square root to get their combined standard deviations. And so the square root of 2.5 for both cases is going to be, I believe, 1.5. Let's do that real quick in this calculator. And there you go. If you look at the distributions, you can probably make a nice assumption that if you go 1.5 units out and another 1.5 units out and so forth, that does roughly translate to capturing about most of the data when you go 3 standard deviations out in both directions. So that does match up with both of these here. Let's get into another example. The diameter C of the top of a randomly selected large drink cup at a fast food restaurant can be modeled by a normal distribution with a mean of 3.96 inches and a standard deviation of 0.01 inch. That seems important, so let's write that out. It's going to be your mean, and that's going to be a mean of C since we're using the random variable C, and the standard deviation of C. The diameter L of a randomly selected large lid at this restaurant can be modeled by a normal distribution with a mean of 3.98 inches. We'll call that one L. So the mean is going to be L, and the standard deviation is going to be standard deviation of L. And the standard deviation of 0.02 inch. Assume that L and C are independent random variables. For a lid to fit on a cup, the value of L has to be bigger than the value of C, but not by more than 0.06 inch. So we have a limit here. Let the random variable D equals L minus C be the difference between the lid's diameter and the cup's diameter. We have two problems, so you might want to screenshot this or pause the video to write these down. A, describe the probability distribution of D, and B, what is the probability that a randomly selected lid will fit on a randomly selected cup? Describe this probability in words. Part A, describe the probability distribution of D. Well, a couple things going for this problem is both of these distributions are normal. So L and C are both normal. They're also independent, meaning they have one does not affect the other. And they're random variables. Because both of these are true, we can then say probability of D is going to be true. So when we combine two random variables, whether we're adding them or subtracting them or doing any sort of scalar multiplication, the combined random variable will be normal if the other two are normal. as long as they are independent of each other. So this independent thing is important. Knowing that information, we can now say it is a normally distributed probability distribution. So D is normally distributed. But in order to describe the probability distribution, we must come up with the mean of D and the standard deviation of D. So the mean is going to be, since we're doing subtraction, the difference between those two means, L minus C. So I have my L here as 3.98 inches, so it's going to be 3.98. And then we're going to subtract the 3.96. So that mean is going to be 0.02. The standard deviation, remember, requires us to square the other standard deviations and add them together and then take the square root. So we do that by using the square root symbol. We take our two standard deviations, 0.02. We're going to square that, and then we're going to add the other one, 0.01. Square them, add them, put them under the square root. Do it all in your calculator, and you can get that answer for the standard deviation. In this problem, you're going to get 0.02236. You can go out a few decimal places. I'm going to go out to the 6. The more precise you are, the more accurate your estimate's going to be, by the way. So now that we have our mean and our standard deviation of our combined distribution, we can now answer a couple of questions. Remember that I added the squared standard deviations because the variability is still going to spread even though we're subtracting those two random variables. Let's look at the next part. Part B, what's the probability that a randomly selected lid will fit on a randomly selected cup? Describe this probability in words. Recall from the problem, it said for a lid to fit in the cup, the value of L has to be bigger than the value of C, but not by more than 0.06 inch. In other words, let's draw out a normal distribution so we can define our boundaries. We'll make our normal curve. We'll do 0.02 in the mean, and we'll do it n 0.02, comma, 0.02236. And let's think about what these boundaries would be in this case. So for L to be bigger than C, that means L minus C would have to be greater than 0. So I would want my boundary to be somewhere starting at 0. And it could be off by no more than 6 or 0.06 inch at the very end. So 0.06 would be somewhere over here. So what I'm looking for is shading between those two boundaries. And once again, we're going to use our normal CDF in our calculator to do the heavy lifting for us. So pull out that calculator and let's get our inputs in. We'll hit up our second vars. We'll do normal CDF. Our lower bound in this case will be 0. Our upper bound would be 0.06. We'll put our mean of 0.02 and a standard deviation of 0.02236. And that probability between those two boundaries would be about 0.7776. We'll write all of these inputs out to get full credit. Now, the answer to this question wants you to describe this probability in words. So remember that this is describing the probability that the lid difference is going to be between 0 inches and 0.06 inches. In other words, the probability that this lid's going to fit on the cup. So let's write that out. I would say the probability that a randomly selected lid fits on a randomly selected cup is about 0.776, or 77.76%. Example 4. Maria likes sugar in her coffee, but not too much sugar. From experience, she knows that more than 9 grams of sugar in a cup make the coffee taste too sweet. While making her coffee one morning, Maria added 4 randomly selected packets of sugar. Suppose the amount of sugar in these packets follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08 gram. What's the probability that Maria tastes coffee tastes too sweet. So no guidance here. When we have to kind of go through the fact that we're doing 4 sugar packets, but this distribution is only 1 sugar packet. So let's think about this. The mean of 1 packet is going to be 2.17. The standard deviation of 1 packet is going to be 0.08. So let's think about combining 4. They're 4 randomly selected. If 1 packet follows a normal distribution, then if they're all random, they're going to be independent of each other. So 4 packets is also going to follow a normal distribution. So we're going to model this with a normal curve. So we're going to do the mean of 4. And that's just going to be 2.17 plus itself, or you can multiply it by 4, and you'll get your value there. The standard deviation of 4, remember, we don't simply add standard deviations, we add their variances. So we do that big old square root. We do our 0.08 squared plus 0.08 squared 4 times, or you could do 4 times 0.08 squared if you'd like. And you get that new standard deviation and mean for the 4 independently selected random packets. Now, folks, I wrote out the things added together separately. Do know that you can just simply do multiplication by 4. Just and the square root, promise me you're not going to square that 4 in this case because they're separate things you're adding together. So it's 4 times 0.08 squared. Anyway, you get your new mean and standard deviation, and now we can do a normal calculation, 8.68 and 0.16. So now we can answer the question. We'll draw ourselves a normal curve with our new mean for our 4 combined packets of 8.68. We'll go ahead and write n 8.68, comma 0.16. Always write that on the top. It's just nice to have that there. Then we're going to do our inputs. So we know this is going to be a normal CDF, but let's talk about the probability we're going to calculate and what our boundary is going to be. So the question is, what's the probability that Maria's coffee tastes too sweet? And it's going to be too sweet when there's more than 9 grams of sugar. So if you think about 9 somewhere up here, who knows where it is, and it's too sweet when there's more than, so we're going to go in the right direction. So we're going to shade to the infinity side. So our lower bound's going to be 9, and our upper bound's going to be infinity. So we're going to do normal CDF. We're going to do our lower bound of 9. I'll just do LB. Our upper bound is going to be, in your calculator, you do a bunch of 9s to simulate infinity. I would just go ahead and write infinity. We'll put our mean of 8.68, and we'll put our standard deviation of 0.16. So let's calculate that. Remember that to simulate infinity, you must do a really large number for your upper. So 9, I put just many, many 9s, and we'll do our mean and standard deviation. And we get a percentage of about 0.02275, so 2.28%. And the probability that that happens is you can do it as a percent or a decimal. I'll leave it as a decimal. And we'll write that out. So this will receive you full credit. Your work showing you to get your new mean and standard deviation, the sketch with the appropriate shaded boundary and your listed parameters, your inputs for your calculator, and your answer. And the answer is as a probability, so it can be either a decimal or a percentage, your choice on this case. Guys, this is a check your understanding. It's probably best that you try to do these on your own. So you're going to want to pause the video, read through the questions, and answer them. And then you can unpause them and I'll work through them. So the question for check your understanding, the amount of liquid soap X dispensed by an automatic soap dispenser each time it is activated can be modeled by a normal probability distribution with a mean of 0.9 milliliters and a standard deviation of 0.042 milliliters. Part A, calculate the probability that the amount of soap dispensed is less than 0.8 milliliter when the dispenser is activated once. Part B, find the 95th percentile of X. Describe this value in words. Some experts suggest that at least 1.6 milliliters of liquid soap should be used by someone washing their hands. Suppose that the amount of soap dispensed on one activation is independent of the amount dispensed on another activation. Part C. Determine the probability that a person will get at least 1.6 milliliters of soap from the dispenser if they activate it twice. Pause the video and try them on your own. We're going to go over part A in 3, 2, 1. So we want to sketch our curve, shade our boundary region. In this case, we want to calculate the probability that it's less than 0.8, and it's only once, so we're not trying to combine this with anything else. So we'll use our mean and standard deviation provided and do this normal probability. This will be a normal CDF. We'll input negative 9999999 to simulate negative infinity, upper 0.8, 0.9 for your mean, 0.042 for your standard deviation. Write all those inputs out. You get a very small probability of 0.0086. So we'll write out our answer and be done with that problem. Let's move on to part B. Find the 95th percentile of X. Okay, now remember, in this problem, you're trying to find, knowing the area below is 0.95, what that X value is. Remember, this is going to be an inverse norm. And then we'll want to describe this value in words. So we'll do our inputs for the inverse norm. Let's go down to paste. The 95th percentile is going to be about 0.969. In other words, 0.969 milliliters of soap. Let's describe that in words. Well, we would say about 95% of the time, the soap will dispense less than or equal to 0.969 milliliters. Remember, a percentile is at or below, so that's why I said less than or equal to. All right, one more part. Part C. Take a minute to read through this and try it if you haven't already. Some experts suggest that at least 1.6 milliliters of liquid soap should be used by someone washing their hands. Suppose that the amount of soap dispensed on one activation is independent of the amount dispensed on another activation. C. Determine the probability that a person will get at least 1.6 milliliters of soap from the dispenser if they activate it twice. All right, we're going to go over this in 3, 2, 1. Well, in this case here, we're going to be combining random variables. But what are we combining it with? Itself, because we're doing it twice. So we're really just doing x plus x. So you're really just going to double your mean. Since your mean is 0.9, your combined mean is going to be 0.9 times 2. And then the standard deviation, you're going to take your 0.042, square it, add it to itself, squared, and then take the square root to get your combined standard deviation. That'll give you a new standard deviation of 0.0593. I like to be very precise on these, so I am going to go out several spots. A couple reasons why I do this, that way I don't have to worry about rounding too much. In the event that I fail to round correctly over here, being off by a little bit is not as bad as being off by a little bit here. So now that we have our mean and standard deviation, since they are independent, remember it's going to be a normal curve, and really just focusing on using our new combined standard deviation. So we're talking about 1.8. You write the n 1.8, comma 0.059397, and we'll answer the question. So the question is asking the probability that a person will get at least 1.6 milliliters of soap from the dispenser if they activate it twice. So we want to shade above, since it's at least 1.6. So 1.6 I know will be over here, and we're going to go in this direction. So this is going to be a normal CDF. Your lower bound, I'll write LB is going to be 1.6. Your upper bound, infinity, since it goes to the right. Your new combined mean, 1.8. And your new combined standard deviation, which is 0.059397. Let's input that into the calculator. We have all our inputs set, so let's go ahead and press enter. And with two pumps, it looks like the probability of getting at least 1.6 milliliters of soap is very high, 0.9996. So we'll write that down. And folks, that concludes our lesson. I hope this was helpful and useful for you for your class. Have a great rest of your day.